Okay, so since there were a couple of basic questions, so maybe from people who weren't there the first lecture, so here is a bit of a reminder hint, right, for number one, which will be if we have a random vector. Here I'm going to use some actually general notation that's going to be useful for me for later. So if you just have a random vector like that, and then you have a subset of the indices, then you can build the subvector XA that only looks at those indices, right? So they don't need to be together. I can just choose the first one, the third one, and the seventh one, right? And then this will be a subvector. And then so this is just notation. So now one of the things that we talked about Gaussians is that the marginals of Gaussians are Gaussian and that conditional distributions are also Gaussian. And that's what you had to use for this exercise. And so these are the formulas, right? So if you have a random vector, m-dimensional, and then you have A and B subsets, and I say they are disjoint, well, the marginal xb, you can just write down, it's going to be a Gaussian of cardinality b, and going to have mean vector mu b and covariance matrix sigma bb. So what does this mean? Well, mu b is going to be the subvector of mu, and sigma bb is a submatrix of sigma, right? So, and I hope these are clear what they should be. Mu b is going to be just look at the entries that are in B. Indices are in B. And sigma bb is look at the submatrix that has rows in B and columns in B. Does that make sense? Right, so you have a full matrix. And if I want to look at sigma 1, 3, 1, 3, well, let's say B is 1, 3, then I will look at the submatrix that has these 4 entries, right? So I would do 1, 3, 1, 3, and that's going to be a 2 by 2 submatrix, okay? And so this will be, since it's going to be principal, it's going to be, again, sigma positive definite, and that's going to be the covariance matrix. And then finally, this was the conditional distribution, which is, if you check everything, it's going to make sense. You think about it as some block matrix, right? So sigma AB is the same. It's the submatrix that has rows in A, columns in B, and you'll see that everything makes sense. This is the Schur complement, and oh yeah, this is actually, I'm missing something here. I just realized. Sorry. I need to fix because it is the Schur complement. So I'm missing the sigma AA. Sigma AA, AB, BB inverse, BA. I had stated it correctly in the lecture, I'm sure. Okay, so yeah, this is the covariance matrix. And a consequence of that, you can think of this as an exercise maybe, is using this, show that a vector, subvector XA is going to be independent of a vector XB if and only if the corresponding submatrix in sigma corresponding to AB is the zero matrix. Okay, so this is a generalization of just 2, where we had seen this for 2. to singletons. Okay, so then that I think if you this should be enough to solve the whole problem 1. And then for problem 2, maybe I just recall 2 definitions for part D and part E. Maybe these are useful. Okay, so this just recalling the definition of the model in G and the vanishing ideal. Okay, I'll then walk around a bit more and then talk a bit about this. Yes, yes. It's so so that was in that particular example where I have the graph into other graph radicals. So then this one may not be, maybe could be if there is a zero, it is easy to see it. but they may not be zero. So that's you need the computation. Yeah. Okay, so let me give the second part of the hints, and then there will be a bit more time at the end to take these into account. So for problem 2, I hope there are no issues with part A or part B, and yeah, I hope this should be, from the definition, this should be easy. If not, then I'll happy to talk to you and see. So now for the last 3, I want to give you some hints. So for part C, the hint is that identity minus lambda inverse, there is a nice expression, right? If you think of analysis, you can compute this 1 over 1 minus x as identity plus lambda squared plus lambda cubed up to infinity, right? And if this makes sense as a series, but it may be true that I already told you, like you can prove that if lambda, so if your graph is a DAG, this is gonna stop, right? And this is gonna be a finite sum, and therefore you're gonna get a nice polynomial. And so that explains why in this MG, if you have a DAG, these are all polynomial entries, because I minus lambda inverse is just polynomials, and this is coming from here. So here the hint would be show that, I mean, it's easier to compute it like this than computing the inverse. Maybe, and then this maybe will tell you something about the paths in the graph. And for example, lambda has all the paths of length 1, lambda squared encodes all the paths of length 2, and so on. Okay? Now for part D, it's a bit harder to interpret, but one should be thinking of the so-called treks. And what is a trek? A trek is something that starts at the top, and then there is a path going down to I and a path going down to J. So this would be called a trek between I and J. So you can go up the mountain and then you go down the mountain. That's the idea here. And so these are called treks. And sigma ij may have to do something with looking at the treks between I and J. Okay, so that's the hint. And for part E, well, ideally it would be great if you do it using Grosvenor basis, using the elimination, right? So using the parameterization here, you can just type it in Macaulay 2, for example, and then compute the Grosvenor basis to eliminate the lambda and the omega, and then you're going to be left only with equations in sigma, and those will be the ones defining this vanishing ideal, Ig. But if you don't want to do the whole setup of Grosvenor basis, there is a shortcut, and that would be using it in Macaulay 2, the package graphical models. So there is a package, you can load it, graphical models, and there will be a function called Gaussian vanishing ideal that will compute this for you. So that's great. That's a shortcut, but you need to still see what do you need to do as an input here. And so that's a good thing to use what Thomas showed us on how to view help in Macaulay 2. So this is Macaulay 2. So you can use this to compute Ig. And finally, how to interpret this, that's the interesting part, right? So as Thomas, I'm quoting Thomas once again, he said, okay, you say Macaulay 2, compute, bam, right? And then it prints out, there is this big output. And then the question is, well, how can I understand this? And that's where the interpretation comes in. And there is actually a beautiful interpretation that I'm going to write here, which is that, well, you can already see that marginal independence you can detect by looking at a particular submatrix of sigma, right? The sigma IAB has to be the zero matrix. And a bit more general condition independent statements can have actually to do again with sigma. So you can see in this example 1, that was the whole point of part B. You can actually read it from looking at sigma. And this is actually a determinant. This is a 2x2 determinant that's coming from 1, row 1, 3, row 1, 2, row 2, 3. So this is the sub-matrix that has these 4 entries. And the determinant of that is 0 if and only if x2 is independent of x3 given x1. And so this is part of a general pattern. And this would be then for E. This would be the main result, which is actually a nice exercise, which is that you can read any condition-independent statement by looking at the submatrix given by A union C as rows, and then B union C as columns. And this must have rank cardinality of C. So this is really great, right? Because this is telling us that, so the rank of a particular submatrix has to be cardinality of C. So this means that all the cardinality C plus 1 minors must vanish, right? So all the determinants of size cardinality C plus 1 will vanish in this matrix. And yeah, so this is a great link between probability, right, statistics, and algebra, right? Because it tells you that you can read a condition-independent statement by imposing polynomial conditions on the matrix sigma. And you can see this is the most general form of this. You would recover this example when C equals empty set. Because when C equals the empty set, okay, then you actually have a marginal statement. And then if C is the empty set, you get that the rank of sigma AB has to be 0. But the rank of a matrix is 0 in this case if it's a 0 matrix, right? So that's how you generalize this. And so for part E, the interpretation, I will invite you to, once you get the generators, to think of them, try to think of them as determinants, subdeterminants of sigma. And then maybe if you find something like this, you're going to be able to find conditional independent statements. Or maybe the other way around. Use your intuition in the graph to think about what kind of conditional independent statements you would expect from looking at the graph, and then see if you actually get those in the ideal. Right? So for example, in this last graph, 5, I don't know how you label how you label these nodes, but I'd say this is 1 and this is 2 and this is 3. Then I would expect that 1 is independent of 2 and independent of 3, because they have nothing to do with each other, right? We know that because this is given just epsilon 1, this will be epsilon 2, this will be epsilon 3, and they're all independent. So these automatically are independent. So that should be reflected in the parameterization when you look at sigma ij. And then in the ideal, this means that in the ideal, the entry sigma 1, 2, so the coordinate, the monomial sigma 1, 2 will appear, sigma 1, 3 will appear, and sigma 2, 3 will appear. Okay, so these kind of things. So you can try to interpret them in terms of these determinants. And so even for 0, I had already given you the answer, right? So for 0, the answer was, maybe I'll repeat it here, right? So somebody has it, somebody remembers. So for 0, what was IG? So let's say, okay, now I'm gonna give you the answer. 1, 2, 3. Someone remember what's the polynomial? And we computed it.
Carlos, there's somebody here. So sigma 1, 2, sigma 2, 3 minus sigma 1, 3, sigma 2, 2. That was
Great.
the binomial.
Thank you. Can you say once more?
Sigma 1, 2. sigma 2, 3
Mhm.
minus sigma 1, 3 sigma 2, 2.
Great. Thank you very much. Yes. So this would be IG, and that's the defining binomial for this particular zero. And that, according to what we just learned in E, or actually it's just the non-standardized version of exercise 1. This corresponds to 1 independent of 3 given 2. Okay, so it's it's not exactly that one, but okay, just change the label. Okay, so ideally, we would like to have this correspondence for each of those graphs. Look at these nice generators and interpret them as conditional independent statements, right? And then we have really this connection between the algebra and the probability. And yes, so I think that's what I wanted to say in this case. And so there was one question at some point about these ideals being toric. So then you can think of them, are they going to be toric or not? As long as you have binomials like this, just 2 by 2 determinants, then you will have, you still have binomials, but once you have a 3 by 3 determinant, you're going to get something big, and then it's not going to be a determinant anymore. So maybe it will not work always, right? So this already happens for graph number 2. You should see.
We label from 1, 2, 3. The first one is 1, 2, then get 1.
0. You want to label them back? 1, 2, 3. Well, you can, but the problem is that then this will break part A, right? Because part A, I wanted a topological order, right? And a topological order meant that if you have an edge, then always the parent has to have a lower number than the child, right? A lower label. So that's why this is the only one that's possible actually for graph 0. Okay, so I think that's what I wanted to say. And I invite you to work on this, a bit more, and we'll take these ideas again in the next lecture on Monday, I believe. It's the next lecture. Okay, so yeah, thank you.
Is there any question or comments? Okay, if this is the case, maybe it might be later on they will ask some question.
Yeah, Dr. Shaheen,
Okay.
there is one remark
Yeah,
from
yeah,
IB.
sure. Sure,
Oh
sure.
yeah, sure.
Okay, so my question is again similar, which I asked in the last session. Think in terms of time series sense. So suppose you have a structural formulation, and in the end, what you get, which is in my point of view, that is actually mimics with the notion of that is called impulse responses functions in time series language. Suppose you have a vector autoregressive model, and then you obtain the impulse response functions. And in those impulse response functions, the coefficients associated with the infinite impulse responses, let's suppose infinite legs, many legs. So we actually learned that the coefficients, the summation is actually equal to 1. So those are actually defined in terms of weights. So if I consider that formulation, and if I consider here the hint you given, like I minus lambda inverse, and that is equal to I plus lambda square, and you actually commented the summation is actually finite, and the summation is always there. So is it not the similar concept, things in terms of the impulse responses weight, where we compute the sum and that sum converges to equal to 1? So those are actually weights. So similar notion here emerged.
Yes, it's a yeah. Yeah, it is a similar notion in terms of convergence and different steps. And you have lags, and how many lags do you have, right? So you compare autocovariances,
Yeah.
If you have a moving average process, then it would be finite. If you have an autoregressive process, then you have something infinite. Yeah. And let me just say that this is actually finite when you have a DAG. Then one of these is not a DAG. You probably realized it's 3, right? 3, there is a directed cycle. So that means that this actually will not be a finite thing, and this will actually be a rational function. Instead of a polynomial, we actually have a rational function. And so this makes things harder. And then you can see why DAGs are preferred, because then to compute this MG, you're gonna have some rational functions appearing everywhere. Okay.
And just a last question.
Mhm.
So in the context of last lecture, you actually imposed topological ordering, and you ignored the existence of loops in your structures. While elaborating graphs. So my point is that think in terms of again sequential model, like in terms of vector autoregressive models. So think like you have a structural model and you converted that model into its reduced form. And while conversion into reduced form, we have observed that there are the existence of loop are there in the structural form. And you impose identification in order to solve the identification problem, you impose the structural decomposition. So suppose if you allow for a moment the existence of loop in your structures, in your causal relationships, and you impose the Kuleski decomposition structure, and in that case, I'm sure in one of your the loop that becomes 0 automatically. So can we allow the existence of loop along with the Kuleski decomposition structure to identify the system, and then we can see how actually the overall structure moves in your setting?
Yeah. So this is a good question that leads into the next lecture, into the next topic, which is going to be identifiability, right? So in the end, we would like to be able to recover the parameters, in this case lambda and omega, from the sigma. If I give you the sigma and the graph, and this we'll see how possible this is if you have a DAG, and how possible is this is if you allow for cycles, allow for loops. And then the answer is will really depend. And I'm just gonna say sometimes you can actually allow loops and you can still recover the parameters you want, identify them, and well, sometimes you can't. And I'm gonna talk about this in the next couple of lectures. Yeah.
Thank you.
Okay, is there any other question or comment? No? Okay, so let's thank the speaker. Okay, now we have a tea break, and after tea break, we will continue with the Professor Thomas Carter. Okay.
So let's meet at 11 o'clock.